In this video, we are going to solve this particular propositional logic problem from discrete mathematics. So there are two methods that you can use to solve this particular propositional logic problem. These compound proposition has a lot of operators, so you can simplify them and prove them using algebraic method. And once you do the algebraic method, you can also verify the answer that you get through a truth table. A truth table will use all the inputs for P and Q, the variables, and give the output. So when you look at the output, you can make some conclusion about the compound proposition like this one. So the algebraic method that we are going to employ and use here to fix this particular compound proposition are logical equivalences. There are some identities. In other words, there are some mathematical identities that we are going to use here. So these identities never change, and they are consistent with mathematics, general mathematics. So the first step is to use the identity and simplify these implications, and we have to convert this implication into something simple so that we can use the negation operator here. Because right now we cannot use negation operator on the implication, because if you use them, then our answer may be wrong. So to change the implication, we use the logical identity called P implies Q is equivalent to not P or Q. This is the identity that we are going to use. So if we use them for the compound proposition P implies Q implies P, then our compound proposition becomes not of not P or, and this part, the whole Q implies P is represent the Q. So it will become Q implies P. It doesn't change, it will remain the same. Now we have to convert this logical implication, we have to convert it into something simple using the same identity what we use here. P implies Q equals not P or Q. So once again, not of not P or not Q or P. Here P remains same, it doesn't change, because Q here is not changing, Q remains the same. Now we have a simplified version of our main compound proposition. So this simplified proposition can further simplified with the help of negation operator. If you use the negation operator on everything inside the parentheses, then we get not of P, and here or becomes and this part of the compound proposition remains same, but we have to negate it. So negation of not of Q or P. Still the parenthesis is not opening, so it remains same. Now there is something called double negation law. So double negation law says that not of P is equivalent to P itself. So we have here something called double negation. So we can use double negation law and we get P. And then we have to use negation on this part of the compound proposition. So negation of not Q and or becomes and, because when we open the parentheses, we have to negate the particular connective also. So negation of or is always and then negation of P. So now we have P and not of not Q and not T. But once again we have here something called double negation. The not of not Q is a double negation, which means our compound preposition becomes P and Q and not T. This is the most simplified version we have right now. But P is on this side, so we want it on this side. It is on the right side, we want it on left side. So we use something called commutative law. Commutative law says that P and Q is equivalent to Q and P, which means it doesn't matter what the order is, the truth value always going to be same. So it becomes our compound preposition becomes P and not of P and Q. Now here what happens is we can see that we can group some of these variables. We can group, and still we are not violating the logic, because this is called associative law. Associative law says that any compound preposition you can group them together if they have the same symbol. If symbol is same, so we have two and logic here. So if we do the grouping of two particular variables, it doesn't violate anything. So P and not P becomes false, because no matter what the value of P is always going to be false. If P is true, the not P is going to be false. If P is false, not P is going to be true. But AND logic says that one of the variable is false, the whole preposition logic is false. So it is false. False and Q is our final output. Now if you observe, once again we have one false and Q, and there are two possible values for Q. One is true and the other input is going to be false. These are the only two input we can give. And no matter what input we give, it is always going to be false. So, which means that our original compound preposition is false. So, no matter what input you give, it is always going to be false, which means it is a contradiction. Contradiction is a compound preposition that will always produce false value no matter what input combination you give. And to verify our claim, we can go ahead and make a truth table and enter all the input combinations for P and Q and see for ourselves, see whether it is true or false, whether this is a contradiction or not. So there are two variables, 1 and 2. So 2 raised to 2 is equal to 4 rows in the truth table. So we have 1, 2, 3 and 4 rows. Now for each row, you have to enter truth value input for P and Q. So P is true, true, false, false, and Q is true, false, true, false. Now using these two values for P and Q values, we have to find the truth value of compound preposition like P implies Q implies P, P implies Q and Q implies P, not of P implies Q implies P. We have to find values for each column, and first one we start with Q implies P. So P is true, Q is false. Whenever Q is false or whenever P is true, this is going to be true. So I will circle each of these rows. So we just simply write true. This particular row, Q is true and P is false. But P is false, so therefore this is false. Now we have to compute Q implies P. So we have a Q implies P column and we have P column. So we can use both of these columns to find the value of P implies Q implies P. Whenever P is false, so let's find all the false entry for P. Whenever P is false and Q implies P is true, Q implies P is true, it is going to be true. So we got true here, we got true here, and this row is also true, and this is also going to be true. So it seems that this P implies Q implies P is a tautology, but we have to negate it everything, and when we negate it we get false. Everything gets false because every entry is negated, so it is a false. So looking at the final output, you can clearly say that our algebraic proof was correct and this is a contradiction. And one more thing we found was that P implies Q implies P is a tautology. So you can remember this, P implies Q implies P is a tautology. So thank you for watching. Please like, share and subscribe my channel.